Hello everyone, thank you for watching this presentation. My name is Goncalves. I'm currently a PhD candidate in the University of Coimbra and one of the authors of the work A Model-Based Approach to Anomaly Detection, Trading Detection Time and False Alarm Rate. In the next minutes, I will briefly explain the key points of the work and hope that you find it useful. This talk is divided in 5 parts: the motivation, the introduction of our anomaly detection mechanism and model, followed the explanation about our experimental setup, experimental campaign and assessment, and the takeaway messages where we conclude this presentation. The motivation of our work relates to the complex computing system as cloud solutions, that is basically virtualized environments commercialized as infrastructure as a service. Those solutions nowadays have increasingly been adopted and are present in nearly every market. Such ubiquity, in turn, is a potential fertile ground for security and privacy breaches. To detect and mitigate attacks in the existing IAA systems is then critical. An approach to this problem is to detect anomalies such as zero-day attacks and advanced persistent threats during the daily operation. The imposing challenges of anomaly detections are: how can we define what a normal behavior is? The fact that the attackers can adapt their behavior to the definition of what is normal in this context adds even more complexity in the context. And how to handle this difficult when there isn't much data available to guide the approaches. So we focus on anomaly detection approaches based on system performance signatures. In this work, we propose a methodology for anomaly detection based on performance deviations caused by anomalies in complex virtualized systems. In particular, we use performance signatures that have the potential of detecting zero-day attacks and do not require detailed knowledge of the attack history. The contributions of the work are an analytical model to support anomaly detection design, a model-driven principal mechanism design that can assist the system administrators to assess the anomaly detection algorithms based on previous data from the system and allows it to control the rate of false positives in a principled manner. An experimentation assessment of the methodology in practice using a publicly available complex system using only non-intrusive user-level performance metrics commonly available in production environments. Let's consider an hypothetical complex system like a brokerage firm that runs on cloud. Imagine that it has internal subsystems, one to handle interfaces with the world, and 2 transactional ones that process different workloads. Many external agents interact with it by thousands of transactions daily, like markets, services, and users. In its daily operation, under normal conditions, without any anomaly in the system, it will have an expected baseline average throughput and its related standard deviation. Those metrics are easily extracted in production and will be the basic metrics that will feed our approach. This hypothetical scenario is precisely the model of our user case, the TPC-XV, which will be explained later. Our performance signature algorithm relies on workload variability and was previously studied in the literature. The novelty of our work is the assessment of the trade-off between detection time and false alarm rate. But how does the workload variability assessment work? As said before, we have a baseline average throughput and standard deviation. The bucket algorithm works by continually comparing the target throughputs with the current sample throughput, maintaining B buckets of depth of D each. The algorithms are tuned by varying the bucket's depth and the number of buckets B. The larger the product D plus B, the smaller the rate of false alarms, but the longer it takes for the algorithm to detect the performance degradation. Notice that the lowercase notation represents the current bucket and the current number of tokens in the current bucket. The target throughput is a function of the baseline metrics and the number of affiliate buckets. Tokens are added to our system as the algorithm processes the current system metrics. A token is inserted in the bucket if the current sample throughput is lower than the target throughput. Otherwise, a token is removed. So let's assume a hypothetical instantiation of the average throughput of 3, standard deviation 1, 2 buckets with the same depth of 4. The first bucket has already 3 tokens, and the sample throughput that is observed in the system is 2. This will imply that a token should be added in the first bucket, and this next sample is also 2, which again will add a token in the bucket. This time the bucket overflows and the pointer moves to the second bucket. This time, to accommodate a load variability, the target throughput is 2. That accounts for the standard deviation. If we observe again a sample throughput of 2, this time a token will not be added, but instead removed. And since this bucket is empty, the pointer moves back to the first bucket. Now let's assume a constant throughput rate of 1. And with this, we will add tokens to the bucket algorithm to the point that the last bucket will overflow and an alert will be raised, which could mean an alarm on the system. Now we talk about our anomaly detection model. The system administrator continuously considers 2 alternative hypotheses: the null hypothesis, where there is no anomaly taking place, and the alternative hypothesis H1, meaning that there is an anomaly. For instance, a system is under attack. The model assumes 4 definitions. The mean time until a false alarm under H0 is denoted by AB of T, and is given the mean time to reach the absorbing state of this Markov chain that characterizes the algorithm. Each transition of this Markov chain corresponds to the collection of a new sample. The closed form for B equals 2 can be found on paper. The second definition is the lower bound of the number of samples until a true positive under H1, assuming all buckets are initially empty. The third one is the probability of false alarm, fully explained on paper. The expected cost of a given system parametrization is a weighted sum of the probability of false alarms computed under H0 and the lower bound of the number of samples to detect an anomaly computed under H1, the alternative hypothesis. The model also assumes that anomalies will change the throughput distribution and will always be detected, and the number of samples to detect the anomaly is much smaller than the number of samples collected before getting a false alarm. Those assumptions are mild and should typically hold in real settings. Our work proposes a model-driven optimization approach, trying to answer the question on how determine the optimal number of buckets and buckets depth so as to minimize the lower bound on number of samples to detect an anomaly. We discuss an optimization method to parameterize the algorithm using an approach with hard constraints. We want to minimize the lower bound of the true positives subjected to target false alarm rate of F. Alternatively, the problem can be formulated through the corresponding Lagrangian. More detail about the model and the optimization approach can be found on paper. To validate our methodology and approach, we run an experimental campaign using the TPC Express benchmark P, which is a publicly available end-to-end benchmark for data-centric workload on virtual services. As you can see in this figure that represents the conceptual architecture of the TPC-XV, the benchmark has many components that interact with the goal to measure the performance of the system. We deploy this architecture in a virtualized environment with 15 virtual machines that are managed by a Xen hypervisor. Details about this deployment can be found on paper. This chart shows the transaction by time of a typical run of TPC-XV. The system has 12 transactions with different profiles. Also, the benchmark models a load fluctuation varying the number of transactions processed by different groups with also different sizes during each phase. As you can see, we have 4 groups here. The different groups are representing this architecture. To establish the baseline metrics, we run the system without any anomaly to characterize its behavior. We will reference those executions as golden runs. From the 15 virtual machines, 3 were used to emulate a malicious users running resource exhaustion anomaly on systems. A third part 2, stress NG, were used to exercise physical subsistence of the kernel and emulate resource exhaustion anomalies as attack. We then established 3 fault models with different intensities to emulate an attack on the system. After we decided to inject those attacks on different phases, on the 4th, where the groups with more resources contribute more in the throughput, and in the 6th phase, where the overall throughput reaches its peak. To calibrate the system, we assess the expected number of samples until a false alarm using the data from the golden run. Using the trade lookup transaction as example, we got the probability of the transaction for the Markov chain as P1 0.46 and P2 0.71. For this, we run the experiment letting V equals 2 and the bucket depth vary between 1 and 30. This chart shows the probability of false alarm as a function of the bucket depth. As the bucket depth increases, the probability of false alarm decreases. For instance, for D equals greater or equal 12, the probability of false alarm is close to 0. Looking at the behavior of the cost function, we can see how the cost varies as a function of the bucket depth also. Those results allow us to turn the parameters of the algorithm. In our experimental assessment, we analyzed the residual effects arising after the injections, assessed the effectiveness of the method, and our focus was on the bucket depth of 12 and 15 as prescribed by the model-based analysis. In our experiments, we observed that the number of buckets overflows after an attack ends was significantly greater than in other non-attack periods. This chart shows the number of alerts as a function of time. Many alerts happen a few seconds after the attack, which suggests that this can happen due to residual effects of the attack. We proposed a simple risk to determine when a set of alerts should be aggregating the single alarm. We accounted the mean time to the first alarm under an attack period and used this value as a threshold. In this table, since we are using the mean time from all failure modes, the higher the D, the greater is the chance of some alarm would not happen, and then the lower value in the column D equals 15 is expected for these 2 transactions. This last chart shows the number of residual alerts as a function of bucket depth. For all fault models, the proposed risk yields residual alerts under high-intensity faults. In addition, the number of residual alerts decreases as D grows. As the larger the value of D, the higher is the tolerance for transient faults. Under the scenarios considered in this paper, the proposed risks do not disclassify any non-related alert. We also evaluated how the parametrization affects performance. Anomalies are detected per transaction and per virtual machine group, over 9 transactions that showed relevant in detection anomalies. This table reports the performance metric from our experiments. We can see that the number of false positives is low as suggested by the analytical model, even 0 for some fault models. The F measure shows how the method has good results exception of the fault model low and short, and consequently degraded, since we account the lower short on it. Excluding this list, we clearly note the effectiveness of the method. To deal with short anomalies of low intensity, we found that D must be fine-tuned. We found some evidence that a transaction-based tuning with different parameterization for different transactions can lead to a better outcome for those low performatic fault models, and these will be evaluated in the future work. In this presentation, we show the effectiveness of the method and also that it captures the trade-off between detection time and false alarm rate. We thank you for watching this video.